al Laboratorio Internacional de Partículas Elementales de la Universidad de Guanajuato. Lo fundamos el año 2005 para estudiar las partículas elementales y desarrollar tecnología de detección de radiación, incluyendo rayos cósmicos. Hemos atendido a más de 100 estudiantes de servicio social, 30 estudiantes de licenciatura, 20 estudiantes de maestría y 10 estudiantes de doctorado. Desarrollamos investigación en tecnologías de detección de radiación. Hemos logrado algunas innovaciones que han merecido premios nacionales e internacionales. Colaboramos en experimentos internacionales de primer nivel. Hemos creado el Seminario Lederman, difundido internacionalmente a través de medios digitales. Ha llegado a más de 1 millón de personas, especialmente jóvenes de Latinoamérica, en 6 meses. Contamos con invitados internacionales expertos, líderes en su área, de primera línea, que exploran las fronteras de la ciencia. Hemos publicado más de 22 libros de divulgación y referencia y más de 100 artículos de ciencia en revistas indexadas a nivel internacional. Los esperamos.
Welcome to the Lederman Seminar of the Cosmic Month. I will introduce Dr. Liang Li. However, I will do a brief introduction in Spanish, and afterwards I will introduce him in English. Dr. Liang, que nos acompaña el día de hoy, representa la colaboración Muon G-2. Recibió su licenciatura en la Universidad de Pekín y su título de graduado de la Universidad de Wisconsin-Madison en el Departamento de Física en el 99. Participó en varios experimentos y estuvo en su disertación doctoral en DESI y en el experimento ZEUS del colisionador ERA. Recibió su grado doctoral en el 2005 y posteriormente se movió a Fermilab, el Fermi National Accelerator Laboratory en Batavia, y trabajando en el experimento D0 en el Tevatron como postdoctoral. Ha promovido la Facultad de Investigación en la Universidad de California en Riverside en el 2010 y se unió al Shanghai Jiao University como un investigador distinguido en el año 2012 y perteneció al staff de profesor de tiempo completo a partir del año 2020. Es cofundador del grupo de física de colisionadores en esta universidad. Lidera esto y la investigación en el grupo de Muon G-2. También participa en el proyecto Atlas, en el experimento del colisionador en el CERN, y el día de hoy nos acompaña con este interesante seminario sobre el experimento G-2. Welcome, Professor Liang Li. Professor Liang Li received his PhD in physics from Peking Beijing University and entered the Graduate School of University of Wisconsin-Madison at the Physics Department in 1999. He performed his PhD dissertation research at DESI on the ZEUS experiment of the Hera Collider and received his doctoral degree in 2005. Later, he moved to the Fermilab, Fermi National Accelerator Laboratory in Batavia, Illinois, USA, and worked on the D0 experiment on the Tevatron Collider as a postdoctoral. He has promoted to be research faculty at the University of California, Riverside in 2010, and he joined the Shanghai Jiao University as a distinguished research fellow in 2012, became a tenured professor of physics in 2020. Professor Li co-founded the Collider Physics Group at g-2. He is currently leading the research group of the Muon g-2 experiment at Fermilab. He is also a deputy leader of the g-2 Atlas Working Group on the Higgs physics and top quark physics topics with Atlas experiment at the Large Hadron Collider at CERN. Professor Li, welcome. We are honored to having you celebrating the Cosmic Month. Xie. Thank you.
Thank you. Thanks a lot for the nice introduction. So I'm very happy to be here to talk about the Muon G-2. So let me share my slide. Can you see my slide? Everything looks good?
Yes, Professor.
All right. So go ahead.
Somehow it stopped sharing your screen, and could you try to share your presentation again, please?
al Laboratorio Internacional de Partículas Elementales de la Universidad de Guanajuato. Lo fundamos el año 2005 para estudiar las partículas elementales y desarrollar tecnología de detección de radiación, incluyendo rayos cósmicos. Hemos atendido a más de 100 estudiantes de servicio social, 30 estudiantes de licenciatura, 20 estudiantes de maestría y 10 estudiantes de doctorado. Desarrollamos investigación en tecnologías de detección de radiación. Hemos logrado algunas innovaciones que han merecido premios nacionales e internacionales. Colaboramos en experimentos internacionales de primer nivel. Hemos creado el Seminario Lederman, difundido internacionalmente a través de medios digitales. Ha llegado a más de 1 millón de personas, especialmente jóvenes de Latinoamérica, en 6 meses. Contamos con invitados internacionales expertos, líderes en su área y de primera línea, que exploran las fronteras de la ciencia. Hemos publicado más de 22 libros de divulgación y referencia y más de 100 artículos de ciencia en revistas indexadas a nivel internacional. Los esperamos. Al Laboratorio Internacional de Partículas Elementales de la Universidad de Guanajuato. Lo fundamos el año 2005 para estudiar las partículas elementales y desarrollar tecnología de detección de radiación, incluyendo rayos cósmicos. Hemos atendido a más de 100 estudiantes de servicio social, 30 estudiantes de licenciatura, 20 estudiantes de maestría y 10 estudiantes de doctorado. Desarrollamos investigación en tecnologías de detección de radiación. Hemos logrado algunas innovaciones que han merecido premios nacionales e internacionales. Colaboramos en experimentos internacionales de primer nivel. Hemos creado el Seminario Lederman, difundido internacionalmente a través de medios digitales. Ha llegado a más de 1 millón de personas, especialmente jóvenes de Latinoamérica, en 6 meses. Contamos con invitados internacionales expertos, líderes en su área y de primera línea, que exploran las fronteras de la ciencia. Hemos publicado más de 22 libros de divulgación y referencia y más de 100 artículos de ciencia en revistas indexadas a nivel internacional. Los esperamos.
El profesor Lee tiene un problema de conectividad y se incorpora en unos minutos nuevamente. Les agradecemos su paciencia.
2021. Was finally when we first published our results.
Results from a laboratory in Illinois suggest that there's new evidence from the behavior.
Fermilab's Muon g-2 experiment.
This experiment at Fermilab in Batavia.
It's called a muon.
Muons?
Muon is basically a heavy electron.
Muons, they have a small hole.
This is actually potentially huge news.
In 2021, we published our first results based on the first campaign of data acquisition called Run 1. This was a dataset collected in 2018.
It still gives me goosebumps to think about that time when we presented to the world what we found out. This was anticipated by the international physics community and still is. That was just the beginning for us, and the world was very excited to know what was going to come from us next. And the quest still continues.
This year, we're releasing the results of the next 2 years of running the experiments. So it's runs 2 and 3.
In 2019 and 2020, we collected more data. This has 4 times the amount of data of the first publication.
We ended up collecting a huge amount of data that needed to go through various stages of our own understanding before we could deliver the result and present that to the world. And so we had loads on our shoulders to deliver. So that brings us to our current publication.
So a muon is basically a heavy electron. It's got a mass 200 times higher than the electron's mass.
They are unstable, so they live only a short amount of time, like 2 millionths of a second. They are relatively easy to produce in accelerator laboratories, and also we can do many tests with them to see if we understand the nature.
In the g-2 experiment, we're measuring what's called the muon's anomalous magnetic moment.
Which just means it's the part that's different from 2. So that's why we say muon g-2, and g is a factor related to the magnetic moment.
Because the muon has a charge and it's spinning, it means it produces its own magnetic moment.
The reason why we're studying muons is that they can probe the standard model, so they can test particles and interactions.
The g-2 experiment essentially revolves around a huge magnet.
The magnet used for the Muon g-2 experiment is a superconducting magnet. It has a 50-foot diameter. We run more than 5,000 amps through it, which produces a field of approximately 1.45 Tesla, which is about 30,000 times the magnetic field of the Earth. So it's a very strong magnet.
Although we're using the same magnet as the Brookhaven experiment, this time we've done a more precise job of making the magnetic field incredibly uniform.
We shimmed the magnet very precisely so that the magnetic field would be as uniform as possible. They wrapped it in what we call the parka, which is the white insulation that you see over the blue magnet. Obviously, bringing it to Fermilab, we also produce more muons, so in that way we were able to take a lot more data.
We have state-of-the-art calibration systems, and many techniques were improved in many cases. So in the end, we'll have a similar statistical and systematic effect, which means that we'll have used the best possible techniques to extrapolate the measurement from our data.
We aim for measuring the magnetic anomaly of the muon to the precision of 140 parts per billion. When you try to measure the circumference of Earth by counting your footsteps while you are walking heel to toe, then you have to count those number of footsteps really precisely. You have to remember those numbers really well. If you miss a few tens of steps, then you immediately lose this precision.
So we blind ourselves to the actual true value of the measurement that we're making in order to reduce our biases. We don't want to be accidentally making analysis choices that will bias the result to what we've done before.
Yeah, so leading up to the unblinding, we were all super anxious, right? We've been doing this analysis for a long time. We don't have any idea what the number is going to be, right? We've done the whole thing without knowing how to calculate the final number here because we've been blind. So we're all sat there in the room, getting together, opening up the envelope, and then we have to punch it in the computer, get it on the plot, and then there's this palpable relief as we see the number pop up there, and whew, it agrees with our last result.
The new generation's taken over. Yes, they did it.
And now for the very exciting part, Dr. Liang Li is back with us, and we welcome you.
All right, let's try this again. Sorry, somehow my computer decided to reboot itself in the middle of this. I don't know why it chooses to do it, at this moment. Yeah, this auto updates. It's okay. All right, so let's try to do it again. Now see this time if it's okay or not. All right, okay. Can you see my slides now?
Perfect.
All right, okay. So I will temporarily turn off my video. All right, I will turn it back on when we do the questions. Okay, all right. So I'm very happy to be here to talk about the Muon g-2 in this fantastic seminar series. I'm Liang Li, as introduced. I'm from Shanghai Jiao Tong University. I'm a part of this Muon g-2 collaboration. So the first question is, when I started all this is our experiment, by the way. And then you can see all these fancy pictures about the particles we're trying to measure, which is the muon. So muon, why muon? Right? It's an amazing particle. So it's unique in this family of elementary particles. This is what we call standard model. You will see the quarks, and you see leptons, and you see the force carriers. There are three families. We really call them a family of the elementary particles, and muon is actually right there. It's a second generation of particles right there. And it's abundant actually. You can actually most of us already have encountered muons, but just you didn't notice because it's so small, right? So it actually can produce abundantly from Earth at the atmosphere from the interaction between the cosmic rays, which is right there, right? Cosmic rays from the deep universe with high energy, they hit our atmosphere, and then they will, one of these, particles it produces will decay into muons, right? Like this. And then it's a sibling of the electrons. Well, you probably heard about electrons before, right? Has negative charge, right? And then, but it's 200 times heavier. And then it's highly penetrating because of the heavy mass, right? So it can actually penetrate a lot of the materials in between and then reach to the surface of the Earth. And it has a half spin. It's a Fermilab, and then decay into electrons. Was discovered in 1936 by Anderson and Lederman, his student actually, from studying these cosmic rays. So you can see this line, straight line, right? As I said, the muons has penetrating power, so that goes most straight. And that's how they first discovered this. And then when they first saw this, they discovered they saw this could be a strong force carrier, right? Was predicted by another scientist, Yukawa. But then soon they realized it's different, right? That's why muons are unique. It actually carries electroweak force only, right? So it is not, it does not interfere with the strong nuclear force. So that was actually quite a puzzle at that time, and a Nobel Prize winner Rabi said a famous quote, "Who ordered that?" Because it's unexpected. So that's almost, the theme of the muon, when we scientists talk about it. It's always come into an unexpected role. It also happens in 1956 when the two Chinese scientists, right, also Nobel Prize winner T.D. Li and Liang, they also suggested that maybe we should look for parity variation in muon decay, right? So that's, the muon's so unique, right? While it's all different kinds of rules, right, has unexpected features. So that's why we want to study it, right? It's like a mystery to scientists. We're trying to find why they're different, why, what's new about the muon. And today I will talk about a feature of the muon, which is a spin, right? So the spin is something, generally speaking, some things rotate, right? You probably see this movie, right? Inception is a pretty good movie. At the movie ending, you see, a gyro that is spinning at the table, and then people wondering whether it stops or not, right? So you can take that as an analogy and see that maybe muon also spin, right? So that's true, right? In the quantum world, particles have spin, right? And there's analogy to the angular momentum in a microscopic world, but it's different, right? It's something rotate, but it's in a different way. The fermions have half integer spins, and boson has integer spins, right? So it's quantumized. It's not a continuous distribution. It's quantumized, and it has only half or integer, right? So that's something different than the microscopic world. And the muon, spin also, denoted as S here. And then this is the magnetic moment of the muon. And you can see that it's closely related to the spin. Once you have a spin, and then you produce, a magnet, sort of, a very tiny magnet. And it also has something to do with these internal structures, because then, depending on how this, the muon spin or how the charge is distributed, then you will have different, magnet. So what we study this then is to study how this muon's intrinsic magnet interacts with the external magnetic field. So as this one shows, right, the muon will rotate or precess, we call, right, because under influence of the external magnetic field, right? So by studying this precession frequency, you can actually infer what the magnet would be, and then what the spin, would look like. So you can actually calculate this one, not only to know the effect of the magnetic field, but also other particles, right? Here I just listed, a bunch of electrons, positrons, but it could be, real particles or even virtual particles, right? The virtual particles can be produced in a vacuum, right? Because of from the rules of uncertainty, right? You have fluctuation, right, in the vacuum, and then you produce virtual particles that can pop in and pop out, right? So these ones can also influence the muon precession. So from all these, you can actually measure this anomalous magnetic moment from theory, and also can measure it from the experiment, which I will show you how we measure in experiment later. So, but then you can have these two things, and then you can compare them. You can compare the experiment and theory, and then see if they agree or not. If it does not agree, then we have new physics, something new. It could be a new particles that you haven't considered that will influence the muon precession frequency, or it could be a new force, like the fifth force, we would call it, right? Because there is an existing 4 different kind of force, right? And this is new one that we call the fifth. Or it could be a new structure, right? This depends on how this the muon itself maybe has internal structure, which we never thought about it before, right? So it's quite interesting to see how these things will, play out in the muon precession frequency. So that's why we're interested to do the muons, and then to check the muon, precession, anomalous, magnetic moment. So we do this at the Fermilab, right? So this is the muon. This is the location of the muon G-2. I think we are right there. And then that was already done, right? We did it like 2 years ago in 2021, right? This is our measurement, and this is the series at the time. And you will see the big gap, right? There is a big gap between these two. And we quantify it by calculating statistically how they're deviate from each other. We, find out that they deviate like 4.2, right? Look at these numbers, right? So, and these are from the previous measurement from BNL, which was done like 20 years ago, right? So from 20 years ago, from 2 years ago, and then that was the combination between these two, and then you calculate the difference between this one and this one, you will see that they have a big deviation, like 4.2 sigma, which means, they have a very high probability of being different, other than statistic fluctuation. So it's big significant deviation. And then at that time there was, said to be one of the top 10 breakthroughs of year 2021. And then we are even invited by Nobel Prize committee to present our results in this, very prominent lectures at Stockholm. So that's first time in particle physics since 2013 Higgs discovery. So it was a very exciting moment at that time, right? But that was 2 years ago, right? So we improved. We actually made a new measurement, now after 2 years. So I will talk to you how much this picture might have changed, after 2 years. So, but before I do that, I first want to show again how this, experiment is done, how we measure muon G-2, right? And this A is how we measure the anomaly, right? This is G-2 divided by 2. This is how we call it G-2, right? This is anomalous because 2 is somehow the standard value, and then any deviation from that is like anomalous, right? And again, this is similar picture I showed you before, but this time I put more particles because it's not only electrons, it could be, pions or even unknown particles, right? And then this is the precession frequency written in this way. So you have polarized muons in magnetic field, and then it will process, and then you can get the precession frequency in this formula. And how you get this precession frequency in, why it's like this is you can actually have the muons right there, right? And then it will actually decay to electrons. You can get the muon spin directions from the decayed electrons, which I will explain in a few more slides, and you will understand how we can measure it, because actually we measure the muon spin actually from the electrons, right? But the muon decay, as I said, has parity variation, so which cause a correlation between the energy of the electron with the muon spin, right? So that's how you can infer that the muon directions from the decayed electrons. And then for the A mu will be the difference between the precession frequency and the cyclotron frequency, because here is the precession frequency, and then since the whole thing is rotated within the magnetic field, the cyclotron frequency, which is basically the frequency the muon moves itself, right? So it can written in this way. It's just because of the Lorentz force, right? So it goes in this way. So you have this momentum, it's red arrow, and then this blue arrow, which is the spin, right? If G is equal to 2, you will see that these two things will be perfectly synchronized. You will not see any anomaly at all, right? So which means these two frequencies will be the same, right? However, once you have a deviation, for example, G larger than 2, you will see that the spin direction will slightly overtakes the other ones, right? Will have a deviation, and then it takes over, and then keep rotating again. So you will see the difference between these two frequencies. At this one, A mu, and A mu is defined in this formula there. So in this way, you can measure the the anonymous magnetic moment of the muon by measuring its anomalous precession frequency, right? So the difference between the two, we call it, anomalous precession frequency. So you can get the omega A, we also call it omega A, and then try to get the A mu, right? So from this one, you can already see that you can try to get A mu, you need to measure omega A and then all these, right? But this electron charge, this mass, and this speed of light, they're all constants, right? The only thing that we don't know is magnetic field. So we actually only need to measure the omega A and the magnetic field, and then we will get to the A mu. So which I will show again in the next slides, right? So just to rewrite the previous formula in this way, the A mu will be proportional to the omega A divided by this magnetic field, and then I expand it to a slightly more complicated formula, but they are all related, right? This omega A is like this, and all these are the constants I mentioned in the previous slide. The only thing different now, you can see that now somehow the magnetic field now transferred to another symbol, right, which is the proton Larmor precession frequency, right? The reason why we did this is because we need to measure this B field, the magnetic field, in very high, with very high precision. So we do that actually using another precession, using the proton, right, which is stable particle, to let it to process within the B field and measure that frequency to infer the B field. But that is completely independent with our muon experiment. So it's a different, measurement. Use a magnet probe, right, with the water sample to measure that. Okay, and then the omega B twiddle is the weighted one because we want it to be the field that endured by the muon. So it also has to be the field folded with the muon distribution, right? Because we want it to be the field, when the muon is present. So I explained all omega A, omega P, and then the others, are the constants, right? As I mentioned in the previous slide. So I will not talk about the details of this, just to to say that those other values, it's already measured by other experiments, right? So we can check the CODATA, database, and it has very high, precision, 25 ppb. 1 ppb is like one of the a billion, so it's a very high precision. So we just take that from the database, right? And then we only need to measure omega A and omega P, right? So to remind everyone again, the final experiment's done in 3 steps. You inject the muons into a ring with a uniform magnetic field, right? And then you measure the omega A, you measure the omega P, and the muon distribution, so you can do the weighted magnetic field, and then you divide this 2, right? Okay, seems simple, but then we also do this in blind analysis, which means we measure it without knowing the final results, right? Try to avoid a human bias. So which means we will have this omega A and omega P done independently, right? So and then before knowing the final answer. So I will show how the blinding was done and how it was opened in the end. So this is how this frequency measurement is done in the method itself. Okay, so maybe I think it's time to stop for a moment, just in case people have questions.
Hi, Professor. Yes, we will take a couple of questions now. One of the participants in several platforms, particularly in YouTube, is asking, who is the strong force carrier predicted by Yukawa that you mentioned in the early slides?
Yeah, that's a good question. That's actually pion, right? So at that time, you kind of predicted this, and of course, at that time, we don't know what the particle would be, right? So but later on we discovered this and then gave the name pion. So the pion is actually a simplest form of the mesons. It's just QQ bar. So it's a quark and then anti-quark in this form. It has a strong interaction with the strong force particles, but not muons. Muons only do electroweak force.
Okay, thank you. Another question is coming from the muons in the cosmic rays. How do you shield from the cosmic rays the experiment?
Yeah, that's also a good question. Right. So yes, the muons will penetrate, right? So it's actually kind of hard to shoot from the cosmic rays, because unless you do this in deep underground, right? So other experiments actually have this. You can do the experiment in deep underground, so you can shield the cosmic rays. But in our experiment, it's not a problem for us, right? Because the reason for that is we measure frequency, right? So that's the beauty of this one, right? The frequency measurement can be done with high precision. That is to say, you have cosmic rays, and then that could enter in our experiment, but it has different frequency than our signal, right? Our signal is the muons rotate within the ring. The cosmic ray does not do that. So it does not affect us in any way.
Okay, thank you. And the last question of this break, about your results. The difference in the results could be attributed to different statistical measures, or to more precision, or did you fine-tune the experiment and change the experimental setting?
It was not clear what was the intention of the question. Is asking about the statistical method of the results, or
the difference in the results. Is the difference in the results due to a statistical fine-tuning or to experimental fine-tuning?
Oh, I see. Okay, so probably it was asking about this picture, right? Okay, so there is a big difference between these two, right? Okay, yes. So that's the reason we invented the sigma, right? So there we see a difference between theory and experiment. So actually, this is a very good question. So, but then you see these two things are different, right? You say, okay, it has a huge gap and they're different. However, we have to also consider the fluctuation, right? Because our measurement has errors. It could come from statistics fluctuation. It could also come from the detector measurement, right? Which means you measure something not so precise, right? So to take into that as a possibility, we actually calculate how much that statistical fluctuation will bring to give the difference, and how much the systematics, or the imperfect of the measurement, the measurement error will bring, right? And we take into all that account, right? And then that's how we get this number. So, and this 4.2 just means the chances that it's purely fluctuation or from the systematic uncertainties, that chance is extremely low. So that 4.2, that roughly translate to 1 out of 400,000. So it's a very tiny probability. So which means you have like 99.99%, as a real difference between the experiment and the theory. Okay, so yeah, I hope that explains why we have these numbers.
Thank you, Professor. If you want, we can continue and take questions in the next break.
All right, I'm happy to continue. So I already explained the principle of this thing, and then next I will show you what does the real thing look like. Okay, you already see the videos, right? So this is the muons, and then you have different apparatus, has different function, right? I will just briefly introduce them. So you have the inflector, which is to bend the muon from straight line to the circle, circlish line, right? And then you have quads to focus muon, so it don't go out of focus, go to other places where you want to focus to rotate within a circle. And then the kicker is to balance it. The inflector is to kick it inside, and the kicker is go from inside to outside. So you have two forces to balance each other to make it go perfectly within the circle, right? So, and then you have the measurement, which is all these ones, tiny, well, it's not tiny, it's tiny, only tiny when you see from this angle, but actually it's kind of, solid big boxes right there. Those are calorimeters, right? As I explained, the muons will decay to electrons, and the electrons will hit these calorimeters and measure, right? And then there's, well, it actually goes in circle, right? So, and then there's MMR probes, right? This is the magnet probe to measure the magnetic field, right? Okay, it actually also goes in circles, right? Okay, so both this probes and the calorimeters they go 360 degrees. And then you take another view of this from top to down view, and then you see all these detectors, right? Different as I already explained, parameters, right? Kickers, right? Inflectors, and then the trackers. I didn't explain. So these are the trackers. We will have two trackers, right? This is to measure the trace of the electrons, right? So I will not talk about too much detail about this. You can read them afterwards. In total, we run in 6 years. That's 9 PB of raw data. So it's a lot of data to analyze. And then I will show you how the muons move in the ring, right? You have this, and then you see how the muons move. Now, first is the computer simulation. Right, you're looking from the eye of the muons, right? You go in circles, like this, and you'll see the quads in the yellow, which trying to focus the muons in the center. And then from actual a camera inside, it moves by this rope, right? It's dragged by this rope, and then you see the camera moves just like muons move. All right, so I hope we're convinced that we have a real experiment. We're doing a lot of fancy things. And then, as I said, it's a lot of data, right? From the 6 years of running, from round 1 to round 6. And we reached our design goal of 21 times BNL. As I said, BNL is a previous, experiment. And the vertical is the how many times more, right? We compare to the previous one. So, we reached that goal. The experiment stopped at the early, this year in July, right? So we have a lot of data. And then, as I said, 2 years ago, we published this tiny fraction of our data set, only 4%-ish. And this time in this talk, I will talk about the blue ones and the green ones, 2 and 3, right? And that's, 4 times more than this one. So that's why our statistics errors are, half, right? Because the statistics errors goes as a square root of the amount of data, we have. So it is reciprocal of the square root of the data. So that means, we have 4 times more than we have square root of 4 and 1 over. That means half of the error. So that means we have a better precision. And then there's more, right? There's 4, 5, and 6. So that will also be 4 times bigger than what we were presented today. So, more data is coming and more precise measurements, also coming. Okay, now I will take, a few slides to explain, why we can say that we measure the frequency so precisely. So again, remember the errors, right? So the spin is the blue one, the red is the momentum, right? The spin is red one and the blue is momentum. Okay. And as I said, G is not to 2, we already know that. So we will actually, this 2 will be, out of synchronization, right? So one will be, the spin will overtake the momentum and then do this all over again, right? So that's why you will see that, there's the energy will have a difference, when the spin and the momentum has different, alignment. When the spin and the momentum are aligned, right, then you will have energetic positrons or electrons, because it's a simple fact, right? Just imagine you are on a bus or on a train, right, and you're through a bottle of water. So that bottle of water will have a high speed if you throw along the direction of the bus or the train, right? And then because it's in the same direction, that's why because it's aligned. However, when you throw something back, right, in a different direction, opposite direction, that object will have a slowest, speed. So that's the reason you will have this up and down. It's because, it's up when it's line, it's down when it's anti-line, right? Okay, so that's why I said at the beginning, like, why we measure the electrons instead of muons, because muons decay, right? It's not a stable particle, it decays. However, from measuring the electrons, we can actually infer how the muons move, right? It's because of this relationship. And this on the right, animation, that's a different way of writing this, right? This is in the we call it energy spectrum, right? However, we can choose a threshold and cut it, and then count how many electrons are over this threshold, and then you can put it on this time spectrum. You will see that this number of electrons will go up when it's lined and will go down when it's anti-lined. So in this way, you can convert your time spectrum, your energy spectrum, to your time spectrum. And why we do this? Because once we have the time spectrum, you can actually infer the oscillation frequency, right? Because this is exactly how you measure, because this diagram is, the time spectrum, which is modulated by the, anomalous precession frequency, exactly. So that's how you can measure, the omega A from this time spectrum, right? This is the modulation. You can fit it or extract it using, different methods to extract this frequency, and that will be your anomalous precession frequency. Okay, so this is omega A measurement. And then you can expand it using a lot of data, right? And this is actually folded, right? Because the muons decay, right? So you will have a decreasing amount of the muons or electrons. So you can actually, that's why you can fit it all in this one run plot, right? So actually this one goes super long. It goes to like up to 600 microseconds or something. But you can always do this as 100 and then fold it back like this and fold it back. The trick you can fold it is because it decreasing, right? So it will not overlap even if you fold it. So, but it's a concise way of making, plots. So you can see all these ones, right? And then you can, use data to extract the, the modulation frequency. So that's how you get omega A. And then I'll go to the omega P, which is, remember, omega P, even though it says frequency, is actually a magnetic field, right? So you can use a probe, right? MMR probes, using MMR, techniques, right? To do that. So you can measure all these, and then you can, do this, probes, put in a trolley, right? And then you, as I explained, right, in the video, right, you can actually make it go in circle and then measure all the different kinds of, magnetic field along the way. And then you can produce this 2D maps, right? And then you can integrate it to have this, integration map. You can see that it's actually pretty, uniform, right? It's, variation is less than 1 ppm, right? And then, but then you have this, the trolley runs, and then you know this is how you do this, right? You just do the measurements, right? And then you also have this fixed probe, which means it's permanent probes, and these are the probes which moves within this the ring, right? But then there is a measurement between these two, because at that time there's muons in this story ring, which you will not be able to measure the magnetic field. Then how we do this? Then we use the interpolation, right? So we measure this one in in different period, and then we interpolate how the field will change, right? And how we do interpolation is you can use the fixed probe to help you, right? Because the fixed probe is always there, right? So that's how you can measure the field, even though when the muons are already in the ring, you would not be able to use the cart, but then you can use interpolation, right? And then, of course, you have to calibrate to make sure all these probes and all these fixed probe and interpolations, they are, they match each other. You can use the calibration plunging probe to do that. Okay, so this is how you can measure the magnetic field with very high precision. Now I go back to my original formula in this way. And then omega A, omega P, and then only thing I haven't talked about is the muon distribution, which I will show you in the next slide. So this is how the muon distribution look like, right? It's, this is a density. It's basically a density function. So we see that actually it's slightly shifted towards to the right. It's not totally symmetric, right? And the reason for that is the beam actually moves, right? It's a beam. It's a live thing. Well, the reason for that is, of course, the muon is not live. The reason why it moves is because the Coulomb force between these two, because between all these, because muons has negative charge, right? It's compelling, each other. However, it also has a focusing force from a magnetic field. So that's how it moves, right? It's dynamic, right? It's compelling, but then it's focusing. Right, so that's why it moves like this, right? So it's beam dynamics corrections, and then you have, optimize your experiment, try to minimize this, this movement. We call it coherent beta channel oscillation, this beam oscillations, right? But it will be always there, right? The only thing you can do is try to minimize it. So you can, and how we do this is you can use a tracker to back extrapolate. Because we have a trace of the electrons, of the positron, right, the decay product, and then you can go back to its original point, and that's where the muons were at that time. So then you can get the muon distributions like this. So that said, it's shifted towards to the right, right? It has something to do with the momentum distribution, right? So that means the muons will be it's not perfect in the in the center of the calorimeter. It's slightly shifted to the right, and then you can get this. This is how another way of looking this, right? This is the same thing. So this is a circle, and this is a circle there. So it's slightly to the right, like this, right? To the outside, right? So this is how you can get to the muon distributions, and then you can do where the muons were located, and then you can convolute that part to get your final calculations. So let's go back to the final calculations. You have omega A and omega P, right? And then now I have all this, but then I added all these, right? Now it becomes more complicated than the simple division of these two. Is because there's a corrections, right? So I will not have time to talk about all the details of corrections, but I can show you, just explain why we need this, right? So there's a E field and up down motion, right? It's because the E field is because we want to focus the beam, more precisely, right? Not only the vertical ones, but also not only the horizontal one, but also the vertical ones. So that will bring the additional complication to our measurement. So we have to correct for that. And then the pitch correction is the muons moves and in a circle, but it also has a small component of moving up and down, right? Because as I said, the muons it not stay in the same location. It moves up and down and left and right like this. So that's how you have a small component of doing this up and down motion, which will cause the spin process slower than the expected value, because expected, well, the expected equation was calculated, assuming the muons will only do these vertical ones, right? So, and then you have other ones, that's the acceptance from the phase acceptance, differential decay, and muon losses. And so this mostly is because something to do with the limited acceptance of the detector, because our detector does not have infinite amount of volume. It can only accept muons in a certain area or a certain angle. So when the muon, let's say, has a different angle which is too large to be catched by the detector, then it will be lost, right? So this one's trying to correct for that. And then because once it's lost, it could have effect in our precision, in our frequency measurement. And then in the denominator, you will have the field, right? Because the field, is supposed to be constant, but once you turn on something, it will take some time to make it to be constant. So you have to consider that. And then there's the quad vibrations, is because this quad will focus on the beam, but it also has a counterforce from the beam, so which will cause to vibrate mechanically, and we have to measure it to make sure that it does not interfere with our magnetic field measurement. And then there's kicker area current, which is a secondary effect from turn on the kickers, a similar thing to the magnetic field as well. So all these has total correction of 622. So it's sizable corrections. So we have to consider that. It's dominated by the E field and pitch corrections. It's sizable, right? But compared to our total value is not that much. So, but still it dominates our systematics. So I will show you how we can improve that compared to the wrong one. So the wrong one are the red ones, right? And the round 2 and 3 are the blue ones. You can see how much they shrink, right? So these are the uncertainty. So these are not the absolute value of the correction, but instead the uncertainty of the corrections. So you can see that, it shrinks a lot, right? We put them in 3 groups: analysis, methods, rounding conditions, and the measurements of the systematics uncertainty itself. So you can also see that from round 1, we have dominated by this red stuff, right? This is the magnetic, field uncertainties, right? But in round 2, 3, they're more evenly distributed. So the major improvements come from, right, different areas. We improve almost in all areas. So for example, the repair damage resistors, we improve the beam storage, right, which is this rounding conditions. We have better beam, basically, right? So you can have, acceptance effect to be decreased by a lot, right? And then there's strong kicker, right? So one of the reason why it's straight to the right is because you have it's kind of weak kicker, so that's why it's tilted to the right. We already improved that quite a lot in run 2 and 3, so it's more centered now, right? And then has smaller oscillations that also decrease it. And then, as I said, is the quad vibrations. You can have more measurement positions to moderate it pretty well. And then the analysis methods, we also improved the reconstruction algorithm to decrease the pi-up, right? The uncertainty. The pi-up, it just means you have 2 electrons hitting your detector at the same time, right? So that will cause disturbance in your frequency measurement, but we can use the reconstruction algorithm to suppress that background. Okay, and then we did pretty well. Okay, so that's the improvement, and then with that improvement, I show you how this overall uncertainty changes. So these are the corrections, the absolute value of the corrections. So this is how I said 622, right? And then these are the uncertainty for these corrections, right? So the uncertainties are smaller than the correction itself, but still the total uncertainty is 215 ppb. And then you have, compared to the previous one, this is round 1. So this is 400, systematics is like 150. and then you can have round 2 increased. The numbers become smaller, means it's better, right? And then you can calculate the ratio. You will see that it's 2.2 increasement. So it's amazing that it's nearly equal improvement. So which means we improve a lot by collecting a lot of data, but we also improve a lot by improving our measurement itself. So that's all 2 times better than before. So which means we can still improve more once we have collected more data, because the total error is still driven by the statistics uncertainties, right? So which means you just take more data and then you'll have better measurement. So the total systematic uncertainty now is 70, right? So it's this number. So that already surpassed the proposal goal of 100 ppb. So this is amazing how we can achieve that. All right, so yeah, let me show this blind analysis, and then we can have a pause. So we have all these amazing measurements, right, with very high precision, but we want to remove human bias as much as possible. As I mentioned at the beginning of the slide, I said we blend it, but how we blend it? How we blend it from ourselves? The way to do it, we do it twofold blind. One is to change our clock frequency. Clock frequency is just how we collect our data, right? There's a basic frequency how we collect data, and then we choose a secret offset. So which means all the clock frequency will have to be subtract that this offset. Then you can get your real frequency. So you can have this 40 minus delta hertz. That this 40 M-hertz is the, as I said, the basic frequency we collect our data. All right, it's something with electronics. There's one way, and then there's another way, which is software blending, which is sorry, which means we blind our when we extract the frequency, we have offset during that extraction procedure itself, right? So we have the twofold ones to make sure nobody can guess the final frequency before we unblind it. And then how we unblind is we actually have a meeting, right? That happened in July, early this year. And then everyone look at all the analysis, all the uncertainties, to say that we understand everything. We know everything by high confidence, right? And then you vote, right? So it's unanimous vote from all collaborators, and then this offset will be reviewed to unblind our data, and then we can proceed to get the final numbers. Okay, I think now it's probably a good time to stop for questions before I review the final numbers.
Okay, thank you, Professor. There are a couple of questions already. When will the last run of the experiment be?
The last round of the experiment, yes. So as I said, this current one is 2 years, right, from round 2 and round 3, right? So there's another 3 years of data for us to estimate, to analyze. So that will be done within 2 years. So that means 2025.
And is the experiment running, or will it shut down?
Yeah, it's already done, right? So this is actually the last, data taking picture, right? So it stopped at the, July 11th.
Okay. How do you keep the storage region, and how do you make the muons to be on that storage region and not have leakage?
Yeah, that's also a good question. So you're talking about the muons, right? Why it moves in this, right? So that's as I said at the beginning, right? That's the beauty of all these complicated devices, right? So you have the inflectors to bend it, right? Because it goes straight, right? So you wanted to transport it to be at the center of this ring, right? So that's how you can use the inflector to transport this muons to be inside of this storage ring, right? But once you have that, right, it has a tendency to go inward. Then you would have the kickers to balance it, right? This 1, 2, 3 kickers to balance from inside to make it in the center of the circle. And then, but all these are still only vertical, right? Or horizontal, horizontal. But then what about the muons actually 3D, right? You could go, spiral and out of this plane, right? How you do this, then you have this, this quartz, right? Okay. Maybe it's quadruples, right? Like this to focus these ones, Q1, Q2, Q3, right? All these to have that to balance that, and also you have this E field, right? To also to have you to focus the beam. So you have all bunch of detectors to make sure the muons stay in the center. But still, it's not perfect. As I said, the muons, we later found out the muons actually slightly twitter to the right. But it's not critical because we can use trackers to trace where the muons live, right? As long as still approximately within the range, we're still okay.
Okay, interesting. Another question that comes from the Facebook page, it says, if the muon has a very short lifetime and it doesn't have the same properties as the electron, how do you keep it confined to be going in circles if it has such low half-lifetime?
The muons, right? So the muons normally, when the muon is at rest, it has 2 microsecond lifetime, which means it stay there for approximately 2 microseconds and then decays, right? However, this time the muons is in high energy, right? It's like 3 GeV muons, so it's traveling very high velocity. So it has this time dilation, right, from the relativity. It goes 32 times more. So it's like 64 microseconds, right? So it will go significantly longer. But still, 64, it's it's long in the in the quantum field, in the quantum world, but in microscopic world, it's kind of short, right? So actually, you lose muon along the way, right? So basically, the muons go in circles, like 1,000 times of circles, and then it goes away, right? So then how you continue with the experiment is you inject more, right? So we call it field. So you have one field of the muons letting go circles crazy like this, and then it gradually decays, right? So you can see from this picture, right? It gradually decays, right? But then you inject more. You keep going, right? Keep going, right? So that's how you can, and these are accumulated plots, right? So you keep adding them up. So that's how you can get the experiment data collected in this way.
Okay, and if you want, we can continue and leave this couple of questions till the end, so our viewers can reflect on the presentation. Thank you.
Okay, all right. So, yeah, I'm almost done. Just to show you a few more slides, and then we can see the final results and then discussion. So, as I said, the uncertainties are pretty good, and then we have all confidence from all collaborators, including myself, right? I think my picture is right there. I was connecting with video at that time. Okay, so, and then before we do that, there's final check, which is called data consistency check. So we want to make sure there's no, mysteries or internal inconsistency within our data itself, right? What is the idea? Well, the idea is you can actually have your omega A and your omega P, right, plotted in 2D, right? And then you can actually slice your data in shorter periods, right? So you can slice like this slice with slice like this, right? And then redo the whole analysis and just to check the numbers. So you will see your, okay, so this is slightly rotated. Now this time this vertical is omega P, but it's the same thing, right? Omega P, omega A. And then, as I said, right, the division of the omega P is the A mu, right? Is the anomalous magnetic moment. So you will see that once you read it this way, then you should go in a straight line, right? Because these two has a strong correlation between these two. So that's actually can be seen from this picture, right? Because because you have slightly two small pieces, you will have large errors, this error bars. But in general, they are still in the one line. You can also just do the division directly, right? You can just do the division and see if they go into a perfect straight line. And actually they are, right? Within the errors, they're pretty good, right? Except a few points which has large errors, right? So, but we didn't stop there. We check all different kinds of data sets. And then you have this overall data sets like this, right? So you can see that all this division between omega A and omega P, they all lie in perfect line, right? Except a few ones which have huge errors. So we say that to be a statistical fluctuation, right? Because it's within like one sigma, right? So it's understandable when you have a small data sets. So we call it data consistency, which means each part of the data agree with the another part, right? So there's no confliction within data itself. Now we can happily to open the box, and then you will see this is from 20 years ago, this is from 2 years ago, and this is from this year. So you can see all three are very well aligned, right? Considering the error bars, they're almost the same. So actually give us ourselves extra confidence that we did something with very high precision. And then you can do the combination of this one together, right? And then you can do a combination between this one and this one to be the world average. So you will see this is our A mu. You see it's very tiny number. It's like 0.001, right? It's like 0.1%, right? But look at the uncertainty, right? Uncertainty is 190 ppb, right? So that's less than 0.2 ppm, right? So 2 out of 10 million. So it's very high precision analysis. So this is the average taking on BNL, and this is from the Fermilab itself. You can see that it's dominated by Fermilab measurement, right? Because Fermilab measurement has much higher precision than the BNL ones. And then you can check the consistency again, but this time you check consistency, with BNL as also. So these are from the BNL ones. Again, this is omega A, omega P, right? This is not division. This is just the number itself. Then you will see go a linear relationship. And this is division, right? Omega A, omega P, divide each other, called A mu. And you will see that this is a straight line, and this is also a straight line. So that looks pretty good. And you may wonder why there's difference between the different data sets, right? This magnetic field, you said it's stable, right? But it changes. Mostly it's because of temperature, right? The temperature changes, the magnetic field will change slightly. But you can look at the numbers; they're actually tiny data shift, right? Even the change is very small. But within the data set itself, it does not change, right? So the data set is divided in such a way that within itself, the magnetic field does not change much. Within the data set, it might change a little bit, but not too much. Okay, and then we're happy to submit our results to scientific journal that was submitted in August, and they were published like a month ago. And then a lot of people, right, including you, right, this media reach, it's like over 7 billion audience. That's like 90% of the human population. It's pretty major breakthrough in scientific way. And then you have different reports from the media. And then, okay, before I conclude, I will show you the comparison again, right? I promised you that we update that picture, but now what did the picture look like? So I will not have time to talk about theory, but just to say that there's a lot of theorists work as hard as our experimental people, right? So they try to calculate with very high precision. They split in different ways. There's a QED, weak interaction, and then there's a hadronic vacuum polarization from the QCD. So basically, generally speaking, they are calculating how different kinds of particles influence our muons, right? There could be QED particles, weak particles, or the QCD particles. And then it turns out that the QCD particles, basically the pions, right, or other mesons, are the most difficult to calculate, right? And their error, it can be like 0.3 ppm, right? So that's like 300 ppb, right? So it's quite significant. So as I said, this picture changed, right? So let's assume that theory stays the same, and then our experiment change like this. Then you compare, you will see 5 sigma. So remember, we had 4.2 before. So that's large frequency. And then at that time, we were very excited, saying, okay, do we find something? Because 5 sigma is the golden criteria. We establish a discovery, which means you can see definitely that the experiment and theory differ, and there's something new, right? So 5 sigma is a magic number we define in our particle physics society. So at that time, we were excited. Maybe it's a new physics now. We have, can we go to Stockholm and collect our prize? But there's new development. As I said at the beginning, we assumed the theory did not move, but actually they moved. So I explained a little bit how it moved. So this is I focus on the hadron vacuum polarization update because that's the part which has largest uncertainty. Remember, from the previous slide. So that's how they moved. So this was the number before, right, from the ratio method, and these are all new methods, a different way. That is called lattice QCD numbers. You will see that except for this one, right, with large errors, which means when it's large error, it will not have a huge weight. And all other with new errors, small errors, they all shifted towards right? Okay, towards right means it's closer to data, right? So which means all these ones has high precision less than 1%, right? But then it has deviation with the old method, like 2.1 sigma difference. So this is something we the series have to understand why the new method differ from the old method in such big gap, right? And one reason is the new method is not a full lattice QCD calculation. It's only an intermediate window. Intermediate window is within a small energy range. So maybe it will change. I don't know. Nobody knows for sure. Maybe it might change when you include a whole range of that thing. Maybe that lattice QCD results will change. But that's not the end of story. There's another part, which is the old method, right? We call the R ratio method. Itself also has some changes. So these are the previous measurements before 2021 results. And these after dashed lines are 2 new measurements. You will see that one measurement agree with the previous one, but there's a newest one, right, called CMD3 that differ from all the rest, with large deviation. So now this old method also has some internal inconsistencies. People are stretching our heads to understand why. So there's a more recent paper from Babar, which is this number, right? The Babar haven't updated their measurements yet, but they're doing it. And actually, SGTU is also part of that measurement as well. And doing that, we discovered that that could explain why there's some difference between the all these different measurements from different experiments. So if you're interested, you can look at that. I don't have time to go into details. So it's suffice to say that there's something within the R ratio method itself to understand why there's difference between them. And there's a third way, which is to not use this new one, not use the old one, use the third way, right? Is to do this hadron vacuum polarization measurement from experiment. It's called Muon E, right? Okay, that's something in the future. Try to improve this measurement. Okay, so but anyway, with all that uncertainty in mind, I updated this figure. We updated this figure. So after this 2021 release. So now the theory moves, the big jump from this one to this one. This is mostly dominated by the old method, and this one is taking into account the new method. It's lattice QCD measurement, right? So that's why you have a huge jump between these two. And now this time the difference is only 2.3. Okay, it's a little bit unexpected, right? So, but still, we have more mystery to solve. There's still a lot of things to do. If you're interested in the theory part, you can read it. There's a fantastic improvement from the theory fund, and there's new results. As I said, Barbara is going to update there. So which means that R ratio method will change as well, right? Then we'll see how this changed results from R ratio compared with the lattice QCD results. So, but there's still hope, right? The reason for that is even though the measurement moves, there's still very significant deviation between these two, right? So that's that theory, this new updated theory, that's our experiment. That's still a very big gap, right? Not as big as this one, but still very big. I say this because we haven't measured the whole data then, right? So the whole data set will, as I said, 4 times more, right? So which means this error bar will shrink by 50%, right? And as I said, the theory is improving a lot, and this error bar will also shrink. Let's say maybe 50% as well. If you take into that account, that deviation will become 5 sigma again. So it's very exciting, and very eager to look into the next measurement of our experiment, and also the next calculation from the theory. And then maybe we'll reach 5 sigma again. So finally, before I conclude, let's introduce the amount of the fantastic team of collaborators, right? We have over 180 collaborators from all over the world, right? From 7 countries and different collaboration institutions, right? And my institution from Shanghai General University in China is right there. And this is one of our pictures. And then this is our Muon team at SJTU, right? We're very young, right? We have 2 faculties, me, Liang Li, and then Kim Xiangkao from the TDI institutions. We're both at SJTU. And then we have other experiments besides Muon GMS2, right? From JPAC, from PSI, and also from locally the Shine X free laser experiment at Shanghai as well. All right, so finally, let's go to the conclusions. So we have the Muon GMS2 measurements collections, as I said. So this is from the July, and then we published 2021, in a round 1, and then now we published round 2 and 3. It's most precise measurement so far, 0.2 ppm, and then the final release will be in 2 years, right? So which is 4, 5, 6 altogether, and then maybe we'll have 5 sigma discovery. So it's very excited to see that. But before that, there's also new physical potentials I no time to talk about. There's Muon EDM, CPU violation, and dark matter searches. All this can be done at the Muon GMS2. And then there's no next experiment, right, which is JPARC increment, which will measure Muon GMS2 in a completely different method to do that. So that will maybe start in 5 years ish, right? It's building. They're building that experiment now. So we are expected to see new results coming from there in the coming years. So that means there's more exciting results from music physics on the way. Stay tuned. We will see new fantastic results from Muons. Thank you. Thanks a lot.
Thank you, Professor Li. Actually, very interesting, and we certainly hope that you can be going to Stockholm really soon. We have a question about what other particles are being found in other experiments, and if such experiments could contribute to your results, if you are aware of some other particles, because in the media there was
for the new particles, there is a big experiment, which I'm also part of it, which is a large hadron collider, right, at CERN in Europe. It's colliding with very high energies, like 13 TeV, right? The muons here is only GeV, and GeV is 1,000 times bigger than GeV. So it's 13 TeV, so it's very energetic. It can produce lots and lots of particles. And people, there are thousands of scientists there searching for new particles there. So far, we haven't found new particles yet, right? But I think it may just take time, right? It just take time to accumulate, because the new particles may be very elusive, right? Which means it may require very high energy to be produced, or it may have very faint decay signature, which is very hard to detect. But both of ways, these things can be improved by collecting more data and look more carefully in the analysis itself. So people keep searching in the larger hadron collider, and there, Muon G-2 can help. Is if we find a larger than 5 sigma discovery in Muon G-2, then we can infer how high that how heavy that particle can be, or how the faint that this new particle may interact with the existing particles. That will give you a direction to look for, where to look for these new particles. Yeah, so I think that's the idea.
Okay. Another question that comes from the Facebook page, it says that if there are any archaeological or technological applications of these findings of the muons, or is there any way to take advantage of these new theories in the technology and industry sector?
Yeah, that's a question I was asked, kind of fairly frequently. So what is, you have this fantastic muons, you have this, even if you have this a discovery, what would have impact in human life, right? So yeah, it's it's hard to articulate exactly what that will influence. I think it's mostly in general in the long term, right? Because let's say from two fronts, right? From theory, if you have this discovery, you have this new physics, that means the model of this the whole universe will be rewritten, right? Because now you will see there's new force or new particles involved in the evolution of the universe, right? Then you will see the universe in a different way, right? So you will have a different theory framework to understand how this the universe will go. Then you will understand the fate of the universe in a much better or clear way. So that's the a general picture, how the theory will affect us, right? So and then from that one you will also predict and then the new particles, how that will influence or interact with the existing particles. You may have even more discoveries, because one thing, right, one new particle interact with the another one will produce even more, right, different effects, right? So that's from the theory. From the experiment, yeah, they have complicated analysis, right, or techniques, right? So maybe I should just go, right? So from all these detector pictures. So one thing is to how you measure, how you do this magnetic measurement, right? So you can measure it with very high precision. So that gives you a way to measure small fluctuations, right? To stabilize the controlled environment in such a way, so you can measure it with very high precision. So I think that's technically that's also very good. And another experimental thing is basically how you manipulate this muon beam, right? You manipulate it in high precision, right? So that might not have direct application to the everyday life, because everyday life you don't have the muon beams, right? But the thing is, you can expand it. You do this, then there's something called accelerator physics, right? So you can have this, then you can make a bigger, right, or more complicated machines, which may help you to do the muon collider, right? So, or another particle colliders, right? That will push you to the, a different aspect of the experimental techniques to make more discoveries, in the particle physics world. So yeah, those are the things I can think about, the applications.
One curiosity that arises is what happens when these experiments finish with these big elements and this big experiment? What happens with all the equipment?
Yes, that's also a very good question. So this equipment, most detectors can be recycled, right? So these these detectors, because it just, for example, the calorimeters just detect electrons, right? So you can disassemble it, right? And then you can take the crystals, right? And then to make it to measurement, do other measurements. That's fine. The soldering itself, right, which is a big ring, that's very heavy, right? That's like 2,000 tons or something, right? That cannot be easily moved around. So I think those are probably will just stay there, right? But then there's a opportunity to say that maybe in the future we can upgrade it, right? Upgrade this one, which means you can have even higher intensity beam, right, of the muons, right? Or you can try to measure different, quantity of the muons, right? Or make muons collide or something, right? So in that case, then this this storage ring may have other use as well, because that time you can reuse it. Those things don't break anyway, so you can put it there, put in, in years it can still be reused. For example, this storage ring was actually disassembled and reassembled from the BNL experiment, right? Which was done 20 years ago, right? But this storage ring can still be used, in the future experiment. Yeah.
Excellent. Okay, we have crossed the time limit, but I'm sure all the audience is really happy about this particular seminar. And do you have final thoughts for our audience, which is comprised by professors, by teachers, and by students from Latin America, and you have greetings from Mexico, Peru, Colombia, and Guatemala.
Wow, it's fantastic. I just want to express my gratitude to be here to introduce you all to the fantastic world of the Muon g-2 and the particle physics in general. So, if you have any questions or other interesting ideas to discuss, feel free to contact me. My contact is, you can Google my name and my institution. You will see my homepage, right? So you will find my contacts there. Or you can talk to the organizers. I'm sure they will be happy to direct your inquiries to me as well. So yeah, I'm very happy to have this opportunity to talk over you. And yeah, and look forward to the next new discoveries of the muons.
Oh, we hope certainly that this is not the last time that you visit the Lederman seminar series. And we thank you. And on behalf of Dr. Julian Felix, the director of the Elementary Particle Laboratory at Universidad de Guanajuato, we thank you again for your participation today. This closes the Leon Lederman seminar with a golden brooch for the 2023 year. And we'll start in January with Dr. Felix Flicker from Oxford, who is going to be talking about magnetic monopoles. So with this, we hope all of you have a happy holiday season. And again, we thank Professor Liang for his